given by h bar omega over 2. Now, as we go up in states, the number increases by 1 until we reach a ladder of n states. And we'll call this one n minus 1 and n plus 1. So what I'm looking to work with mainly here is our A dagger and our A. These are the operators that we're almost exclusively going to be working with. I will introduce one more, but that will be the key component. Now, we are going to be working in the n state basis. Now, this is, we're going to call it the photon number state, because in our example, we're using them to represent photons in the field. Now, we'll set it up such that the following eigenvalue equation holds. We have n hat acting on n equal n, n. So n here represents the number of photons in the field. Like so. Now, as I said, the operators that we are almost exclusively going to be working with over the rest of this lecture is going to be A dagger and A, which are the raising and lowering operators. So I'm going to move this down. Now, we want to see how these act on the number states, and later on, we're going to see how they act on the coherent state. But they are the annihilation, which is just A hat, because it's an operator. And we have the creation operator, which is A dagger. So these are the operators we'll be working with. Now, these do not commute with each other. So they have the commutation relation. A dagger equals, and we know that the commutator of two commutators, A and B, is AB minus BA. So we have A dagger minus A dagger A. And in this case, it equals 1. So that is a key point to remember throughout the rest of this talk. Now, we want to see how these states act on the number states. So we're going to have A acting on it. Now, A acting on it, if we have a photon in the nth state and we apply A, it essentially annihilates a photon in the field, so it lowers the state by 1. So we end up with n minus 1. And you can show this after, but it also pulls out a factor of root n. And that's what you need to remember. And we also have A dagger acting on n. Now, conversely, A dagger creates a photon and it raises the state by 1. Oops. So we have root n plus 1 and it raises the state by 1. So these are the first key results that I would like you to remember throughout the course of this talk, because we'll find out that these can actually take us quite far. Now, another aside, because we'll see that for the photon number states, it is the case that if you take the inner product of the nth state with the nth state, you'll end up with a Kronecker product, which means that it is 0 when m is not equal to n, and it's 1 when m equals n. Now, we
Kronecker
find that is
delta?
not a
Just a
property.
thing, Kronecker delta, not product.
Aye, true. Thank you. Well, Kronecker delta, it's a delta. But anyway, that's the case with the number states. We'll find that's not the case with the coherent states. Now, over the course of this talk, since we're going to be looking for a classical EM field, we're going to want something that oscillates in space and time. Now, we're first going to look at some properties of the number states. And the reason why I'm introducing these will become clear as we move through the talk. So, sorry, I've messed that right up. So some properties of the number state. n. Now, first, we're going to calculate the mean, the square of the mean, so that we can calculate the variance. And we're going to be repeating this process because each time we can get some more information about the states that we're working with. Now, calculating the expectation value in quantum physics is something that you do quite often, the variance also. So we'll start off by calculating, and I should say, I realise I have not told you, but I thought it would be clear. So in equation 1, we have h bar omega a dagger a plus a half. Now, in this case, n equals a dagger a. N is the number operator, such that the number operator acting on the nth state pulls out the eigenvalue n. So I should have said that earlier on, but it's there now. So we're going to look at the expectation value of the number operator in the number state basis. Now, to do that, we just use Dirac notation. We take the sandwich of brat n with the number operator in n. Now, I'll show you how I would do this fully at first, but later on, I'm going to be going a little bit faster. Right, so, okay, I was just looking at the chat. But the way, so we know that n acting on n pulls out the nth eigenvalue, and it gives us the inner product n. Now, by the Kronecker delta, this equals 1, so this simply equals n. So this is the mean value we've just calculated. Now, we're going to calculate the square of the mean next in order to evaluate the variance. It's the same process, only it's n squared. In this case, n acting twice on n simply gives us n squared. And this is the mean square. Now, these two quantities allow us to evaluate the variance in the number state base, which is simply given by the square of the mean minus the mean squared. So if we do this, we find that we n squared minus n squared. So I'm taking the n from here and squaring it, which is the second term. And we have the square of the mean, which was n squared anyway. So we see in the photon number basis, the variance is 0. So we have certainty that there are n photons in the field when we use that. Now, what we're wanting to do is find an electromagnetic field. So we're going to introduce a new operator, and it will be the last operator that we use throughout this talk. We're introducing E of chi, which is the electric field operator, and it's shown here without. It's given by a e to the minus I chi plus a dagger e to the I chi. All right, and this is the electric field operator where chi equals omega t minus k dot r minus pi over. What this chi equals should be familiar to a lot of you. This is what you see in an EM wave. It shows, like I said at the start, that we want something that oscillates in space, the k dot r, and time, the t. So this is what we're going to be working with. So I introduced the number states because this represents photons in the field. So it's a great first candidate in order to see if we can get a classical wave out of the quantum state. So in order to do that, we're going to have again the mean, but this time of the electric field operator in the number state basis, which is why I denote the subscript n. And we're just going to evaluate this and see what we get. Now, we're hoping to get something that oscillates in space and time. We'll just have to see. So a half is just a scalar. We can pull that out the front. Now, what we're going to be doing is sandwiching the operator in between. And now, direct notation, it is distributive. So I'll write it out like this, but in future I might skip it. But we can distribute this to get two expressions. And we have a dagger. Okay. Now, what we're going to do here is act A onto the ket state, and we'll act a dagger. Now we know the bra remains unchanged, but we do know that A is the annihilation operator, so it lowers the state by 1. Similarly, a dagger increases the state. Now, we know that these states are orthogonal, so this goes to 0, and this goes to 0. So our end result is 0. Now, that's quite a puzzling result because we were hoping for something that
Hmm.
oscillated in space. So I guess that means this does not seem to be a strong candidate for the electric field. A does not act on chi, so operators act on states. States are defined by the bra or the ket. I have answered your question, but just remember, folks, that there is a slight delay, so I will go back to your questions as I see them. Let's keep them in the Twitch chat instead of the whiteboard because it will make it easier for me to see. But so if you take some operator and you act on the state, you have to act operators onto the state. What that does is it affects the state. In this case, it pulls out a coefficient of root n and it lowers the state by 1. Now, when we look over here, we act it on a state to the right. Now, you can also act states to the left, but then you have to take care if these things are Hermitian or not. But essentially, it acts on the state. So the chi is essentially just constants. The e to the minus I chi and e to the I chi are just scalars. They're not affected. So I hope that was clear. Now, the reason we got 0 shows that the electric field and the number state basis is not well defined. So what we're going to do is move on and evaluate the variance this time, and we'll see what we get. So in that case, we do delta, okay, the variance, which is standard deviation squared, and this is on a number basis. Now, this is going to be minus squared. Now, we know that the mean squared is 0, so we just ignore the second part of this term. The first part, just remember our definition. We'll write it once more. Of chi was a to the minus I chi plus a. So what you have to do is square the electric field operator, so
Strife,
we get a
could you
quarter
lower
out
the
front.
sensitivity threshold of your mic? You're cutting off very
Lower.
slightly.
Right, okay.
Right, like we won't mind if we hear a tiny bit of static from your mic, but you're
No
occasionally
worries.
cutting off slightly.
Right, I'm keeping my eye on the bars. I have it lowered. I'll do test, test, test.
Yeah, this is fine.
Tell me how the test
Yeah,
sound.
yeah, the test sounds fine. So yeah, you can
Oh,
continue. I'll let you know if something's up.
no worries. Thank you.
Yep.
And you were right. Thank you. The square. Forgot the square. But anyways, we're only evaluating the first term. Now the first term, again, we sandwich it. Now what we're going to do here, I'll move this down. We're just going to square it out, then distribute everything. Now I'm going to, the one sandwich, technically you've got four. People say I've got quieter. Hello?
Uh,
Hello?
definitely sounds fine to me.
Hello?
It
Strange.
sounds a lot here too.
Right, I actually changed it up this. Right, okay. So is this any better? Maybe I moved it the wrong way.
Yeah, listen
So
listen to Discord. Listen to Discord. Do not listen to the Twitch stream because that is dependent on the voice input
they
variable on
actually
OBS.
they actually said that well that's what I was changing. I was altering the voice input, so I've increased it this time
Oh,
because
okay,
I
okay,
did it
okay.
the other
That'll be
way.
better. That'll be
Everyone
better.
says it's much better now.
Okay, cool, cool,
Yep.
cool, cool, cool.
Thank you folks for letting me know there's something wrong, so keep it up. But anyway, excellent. So we're gonna square this. So we're gonna end up with the first term squared, which is just two annihilation operators. Is two I cap plus 8 squared, 2 I chi. And in the next line, we'll have plus A, A dagger. The exponentials cancel plus A dagger, A. And this is acting in this expectation value. So we know just by the same process of evaluating the mean, if you apply A twice onto the nth state, it's going to lower the state by 2, but the states are orthogonal. So the first two terms go to 0 because one raises the state by 2, the other lowers the state by 2. So what we have is A dagger, say dagger A. Now at this point, it's helpful to remember the commutation relation. So we know A dagger minus A dagger A. And what we can do is rearrange for the first term, this term, and we'll exchange that. So when we rearrange that, we get 1 plus A dagger A. So we have that, the variant,
Bish.
to a quarter n, and we would end up with 1 plus A dagger. Now, A dagger A is equal to n, and we know that n acting on n just pulls out an n. And the other term, the 1, it does nothing, it's just equal to 1. Plus 2n. Rearrange that slightly. I'll pull out a factor of a half, and you have half. So this is quite interesting. The mean of our electric field operator on the number basis doesn't seem to give us anything, but the variance gives us something. Now we have a half n plus a half. Now note, even for n equals 0, that is when we are in state. There are still fluctuations. So I think this highlights that we're actually working with a highly non-classical state. So maybe it's a little bit too far-fetched to pull in our electromagnetic wave that we're looking for. But I think this is due to this. So this shows fluctuation. And the highlights that we're working
Audio
with a non.
stuttering a bit.
I just saw. I'm not sure why, but my computer lagged a little second there, so I'm hoping it fixed itself.
It's significantly better now again.
Continue, and if it keeps continuing, I can stop and have a look what's going, which signifies we are dealing with a non-classical state. Interest, but the reason we calculate all this is because it's while the photon number states are supposed to represent in the field, they do not give us a good classical description. So we need to look for something else in order to find it. So at this point, what I'm going to do is introduce another set of states, and this is the set of states that this was named after. Is this because classically you'd expect both to be non-zero? No, it's we actually we the main thing is we expect the mean value to be non-zero. Now you're right, actually. I should explain that a little bit more. So if you recall back, when we calculated the mean and the variance of the number states, we got the mean was n, the variance was 0. Now, so thank you for asking that question. I should have been clearer. Now, the reason that the number states are not a good is because while we have certainty in the photon information about the phase, so we have a completely undefined phase. Now, what that means, once I finish writing this, now what that means is that the probabilities of all the states are equally likely, and so they cancel each other out. I think, which is why we end up with a zero expectation value. It's because all phases are equally likely, and therefore they all cancel each other out. So the key thing to note, and thank you for asking, is that while we have certainty in the number, we give up having information about the phase, and that is one of the main reasons why they're not good for our descriptions.
For those
But
who
the number
want,
states,
just a
oh,
quick aside, if you're actually interested in this, um, you will notice that the number and phase are conjugate variables, exactly like position and momentum. So they will follow Heisenberg's uncertainty principle. So when you
yep,
have completely defined a number, as you do for number states, you have absolutely no information at all about the phase, right? So that's a very nice way of thinking about this. If you want to look into it more, just look into number and phase being conjugate variables.
excellent, thank you. So that is why the number states are failing to be a good description that we are after. And I hope I cleared that up. Thank you for asking the question. But we're going to move on to the coherent states. Now, coherent states have been around since the advent of quantum mechanics. Um, I read a paper that stated that Erwin Schrodinger actually knew about the coherent states as minimum uncertainty states of the quantum harmonic oscillator. I'm sure a lot of you know of it by that description too, if you have heard of the coherent states. Now, so uncertainty states of the quantum harmonic oscillator. Now, these were discovered way back in 1960, although they were not seen for their value in their use. I would say until this was Schrodinger. But it wasn't until 1963 when Roy J. Glauber wrote his paper, and I'll link the paper after, that showed the properties of the coherent states being really useful, and we're going to see why just shortly. So that would be 1963, R. Glauber. Now, we find these states as right eigenstates, and we'll see an equation format in just, but it's right eigen of the annihilation operator
Very quick aside,
eigenvalue.
Strife is making the
We're going to call
difference
it.
between right and left eigenstates here because the creation and
Yep.
annihilation operators are not Hermitian, so they have two different sets of eigenstates.
Sorry, it's been a little bit slow. There we go. Now, this is a definition in words, and Cronin was right to make the distinction. So these are right eigenstates. So they apply to kets, not bras. And we'll see why that matters shortly. So in equation format, we have right eigenstates of the annihilation operator with eigenvalue alpha. Now we're going to denote the coherent state alpha, which is the common notation. It's an eigenvalue equation, so it has a coherent state. Oh, whatever Cronin said was not audible in the stream. Okay, so what Cronin said was that I'm making a distinction to be careful by saying that these are right eigenstates of the annihilation operator. That means that these act on a ket, not. So that is what I'm saying. So this is probably going to be the most mathematical part of the talk, but um, it's a really nice derivation, I think. Now we want to figure out what a coherent state is. We know this eigenvalue holds, so we want to evaluate what it is. Now, first we need a basis for which to have the coherent states in. Now, the coherent states, the reason I introduced the number states is that they form a complete set, which means that they're perfect for using as a basis for your other quantum states. So the number states, form a complete set. And what this basically just means is that they fully account for, you can fully describe something in that basis. Therefore, what we're going to do is we're going to let we don't know, we're going to let it be some sum to infinity. So over the full number state, some coefficients that we don't know yet, they're to be determined, and then our state n, our number states. Now, what we're going to do is apply this to equation one. Now, equation one is a very important equation. It's worth remembering. Right. So we're just going to apply what alpha is, k alpha to be clear, to infinity, a acting on n, and that equals alpha, the summation from n equals to infinity summations are important. Cn. If you recall back at the start of the term, we know what A acting on n does. It lowers the state by 1 and it pulls out coefficient root n. So what we're going to have here, the sum of Cn root n lowers the state. Now, if you think about the harmonic oscillator, if you have read Griffiths or any other quantum mechanics textbooks, you know that if you apply the annihilation operator in the ground state, you get nothing, you get an answer of 0. So we're going to change the summation from 0 to 1 here to account for that for n equals 0 to infinity of Cn. Now, we want to derive the coherent state alpha. Now, in order to do that, we need to determine the coefficient Cn. So what we're going to do at this point is compare the coefficients left-hand side and the right-hand side of the equation. That equals, now, starts at n equals 1, as the right-hand side starts at n equals 0. So we can call the right-hand side the n minus 1 state. Now we can rearrange for Cn expression. Now, we don't want to be dealing with every coefficient at every number. So what we're going to do is we're effectively down the states to C3 alpha over root n C3.
Strife, hold
Now,
up for
if
a
we
sec.
ladder
Hold up
down
for a
to
sec. Could you
C2,
just repeat what you just said again?
what part?
Just like the last, I don't know, 10 seconds.
Right, okay. So what we're effectively is we're in order to find this, we want to look for this in terms of one coefficient. Now, what we can do here is because the right hand side is Cn minus 1, we can keep dropping down until we reach the ground state. Now, we would have to do that n times. So what we get is alpha to the n. And once we reach the bottom, we end up with C naught. Now, the reason that happens, the root n factorial, is because you have root so on all the way down. So this is us essentially found what Cn equals in terms of the ground state coefficient. So what we can do is we can rewrite alpha, which was equal to the to infinity of Cn, the sum from n equals 0, substituting what we have, alpha to the n, n factorial. All, it would be a lot nicer if we could evaluate what C naught is as well, because then we'd have a complete description of our coherent state. So at this point, we're going to impose some conditions coherent state that we've just derived. Alpha, they want in quarter states to be such that the inner product equal to 1. Alpha, alpha. So we're going to evaluate this and see what we get out. Now, we have a description for the coherent state that's almost complete. We just want to determine. So we can do alpha, alpha, which is going to be equal to, when you take the conjugate, when you take the bracket, you need to take the conjugate of all the components. So we're going to end up with a C naught star, C naught. We're going to get the sum over n. Now we need to summation indexes. We're going to have two summations. Then we're going to have alpha star to the m, factorial, and see how it's going to turn out. And we have m. Therefore, the summation over n and m just becomes a summation over 1. So what we have is c naught squared, the sum over n of now alpha star alpha, just like c naught star c naught is alpha. So we have alpha to the n factorial, and this equals 1 because we want it to be normalized, remember. I'm hoping some of you are looking at the expression, thinking it looks familiar, but to those who are not sure, we have the e is equal to the sum over n in our case mod alpha squared. Therefore, we have just an exponential c naught squared to the alpha squared. Now we're going to rearrange, so we're going to divide through, and then we're going to take, and we see that c naught equals e to the minus a half mod. Started with an eigenvalue equation alpha. Now we'll let alpha position in the number state. We're putting that all together. You can see that.
Strife, could you repeat the last 6 or 7 seconds? The reason I'm asking you to repeat this is because the audio is stuttering a bit.
I'm terribly sorry. So we've evaluated a coefficient C naught that we look to describe. Now, what I was saying was we started with the eigenvalue equation here that I've just underlined. Now we let alpha be written in some basis that we know is complete, and then we evaluated a coefficient C for our coherent state. Defined because we've just arrived e alpha squared. Now I'm pulling this out front. It doesn't affect to infinity. And I see your question, but I'll just finish writing this. Factorial n. Now I'm just going to move this down. That was probably the most mathematically demanding part of it, but I feel like it's a nice derivation. It's nice to show. Uh, can you start with the function representation of A and solve the differential equation to get the states? I think that you can. I couldn't tell you how to do it on the spot, but I think that you're right. The paper that I spoke about by Glauber, written in 1963, I'm going to link that at the end of this. He goes into the coherent states with a lot of the properties that I'm describing here. If you look in that, you should be able to find what you're asking. So I will link it after and you can see. Now, this is our coherent state. We know that. So we now have this equation as well. And now, A and A transposes of each other. Now, they're not Hermitian. of each other. Then what we have out that if we act now, what this means is that if you take the conjugate of A dagger, similarly, if you take the conjugate of A dagger, you get A. What this means is that if you act A dagger on a brass, which is the conjugate, the joule, just changing the coefficient. Now, these are the key results that I would like you to remember when, if ever you become to work with coherent states, you'll find definitions. The coherent state properties about the coherent states, which we're going to see. So at this point, we want to go back and look at some properties of coherent states because I'm not just introducing them for the sake of it. Like, we want to see, are these a good description to find a classical electromagnetic wave? Now, what we're going to do, now, we know that they're normalized because we imposed that condition in order to find C naught, if you recall. You also find out definition of the coherent state. You evaluate the inner product squared of two states. You don't. This shows that the coherent states are orthogonal. I would recommend that if you're curious, you actually evaluate this and see. As you can imagine, it's a negative exponent. So when beta minus alpha, basically orthogonal. So it's quite an interesting property. It could be another reason why they were overlooked for so long, because more often than not, when you work on a basis in quantum mechanics, your states are normalized and they're orthogonal. They're orthonormal. But it's something to note, and it's quite an interesting property, but it doesn't actually affect your ability to do calculations with them. Now, what we're going to go back to do is evaluate the mean, this time in the coherent state basis. Point we created just before. I'll go back and show you them in just a second. But we n is equal to A dagger A. We can act A dagger using. So what we're going to pull out at this point is an out start from A dagger, and we're going to. Now it makes sense to do what we've done before and evaluate the variance. So we're going to calculate. Now we're going to write n squared, but we're going to use the definition A dagger A. Now this out like this is because I want ordering of important in quantum mechanics. So dagger A act left, and so we have a problem because now I'm hoping some of you can think about this, but sure. commuters to the rest. A dagger. So what we're going to do is plus A dagger A. Get alpha A dagger plus A dagger A. We know that they're just dagger acts on the left. So we get this time we do so we get alpha info number in the coherent state basis. And this is going to be squared of iron, but there's always a distinction. And what we get plus minus to the 4 equals alpha squared. We the number. Some of you, this should be, but when you have a situation, in this case,
Strife, your audio is really stuttering.
now this is it dropping?
Yeah, it's dropping sometimes, and sometimes it's really clear.
There's nothing I can do, man.
I mean, it's really clear
You've
like
got what to say.
right now, so which is kind of strange, but yeah, it's fine.
I'm sorry, man. We're just gonna have to go with it.
That's
I'm
fine.
sorry, folks,
Yeah, it's fine.
but I'll try and speak clearer. I've moved the mic a little bit closer to my mouth. Anyways, this means we have a Poisson distribution. Now, I've read some papers about photon statistics, and they're all done using Poissonian statistics. You know, the fact that it's a Poisson distribution has a lot of good properties. You get really strange stuff like you get sub-Poissonian and super-Poissonian. Sub-Poissonian statistics is quite difficult, but it's quite confusing. But it basically means that you're dealing with highly non-classical states of light. You know, like think about a stream of single photons equally spaced apart. You don't get that classically, but this is something that you can build in a lab now with quantum dot devices, that single photon devices, sorry, that emit photons. It's super cool. It's really interesting stuff. But anyways, is this a Poisson distribution? Well, we're going to find out. So we know that the variance equals of that projection of the equal to, and we write our definite state a half alpha squared because I've used well mod. Since we're projecting only the nth state, the summation that disappears. So e now minus a half alpha squared is e to the minus alpha squared alpha n factorial. Back to these was one at this point. Had alpha e to the fact. Now what you see here, Poisson distribution. I just thought I'd introduce that as well. But yep, Poissonian. So if you ever learn about Poisson statistics, you can apply these all to working with photons and light, which is really pretty cool. Now, we evaluated mean it was we oh dear, N bar. Now, if we look at the relative fluctuation, we take standard deviation, square this to N bar. Now, this is so what this says. The fluctuation is the mean photon number. Back to C class. So it shows. So as we're going to introduce the electric field operator once more. Now we're going to reintroduce, and this is our front of the end. Now we're going to reintroduce field operator to the e to the with equal to omega t. Oops, minus. Sorry, it's been quite slow. And what we're going to do is evaluate the mean value and see if we get something that is non, and preferably something that oscillates in space and time. So we evaluate E and the coherent. Now again, if it's just a scalar, we pull that out the front. Now we have alpha e to the minus I chi e to alpha and act them on each, but we know that we're not going to have problems with orthogonality or just lowering the state. On the right, because you're allowed to do that, is they're not. There's no altering issues here because, and what we're going to end up with is we're going to pull out now A acting on alpha, e to the minus I chi is just some coefficient acting on bra alpha is alpha star. The I. This is non-zero. It's good. Now we're going to do a wee bit of trickery here just to actually show what this state represents. Now we're going to let alpha equal e to the theta, and we're going to let alpha e to the minus I. Now it's coming in, but I'm about to release a problem after this talk about a way that you can view the coherent states. Now you can view the coherent state as a region in phase space, a minimum uncertainty region in a phase space, which is over real and imaginary axes. So this is justified, and if you are interested, there will be a problem after for you to try. I think it gives good intuition about how to view these states. But anyways, I'm going to substitute this in. Now mod alpha is a factor for both, so we pull that out the front over 2. Then we have minus I minus theta minus theta. Before looking at this and seeing something familiar, So what we have here, hmm, the stream seems to have paused.
It's still active for
That's
me.
fine.
I can see it.
No, it's good. I just thought it was. But yep, I'm just seen it. So what we have is cos x a half plus e to the minus x, x equals chi minus. So we minus theta, and then we're going to this step. We're just do. So if here time of omega I theta. Now, this wave the oscillate should. What we find is not only defined, but it also represents a plane wave, which is pretty much how we describe classical EM waves. So often now this was what I was. I hope you have found it interesting. I think the results quite interesting. You've the way I like to think of the coherent states are that they are the most classical quantum state you can get. You know, because it's a quantum state that has a classical limit, both from relative fluctuations decreasing as n bar increases, as the mean photon number increases, and down at the bottom, where we find that they also resemble a plane wave, which is commonly used in electromagnetism. And I'll finish up there, and I'm happy to take some questions. And I hope you enjoyed it, and I hope it was helpful and good. And please give me feedback. Please ask me questions, and I will try my best to answer them. So thank you everyone for joining. Oh,
Nice.
Nice.
All right, I am going to stop recording now. Is that all right?